Okay, amazing. Let's get started. Today we're gonna talk about binary search. Amazing. Okay. So what is binary search? We can start by we can start by giving you the link to the slides. So if you want to follow along on your laptop, feel free, or you can just look at the screen. Okay. And then so this is basically what we're gonna go over. First, we're going to talk about general binary search, and then we're going to give you binary search problems. And some of them may not look like binary search, but they actually are in disguise. That's why we want to talk about them. And then we're going to talk about more advanced problems you can solve with binary search. For example, monotonic functions. And then we're going to talk about binary search trees, which are super fun. Okay, so let's have a motivating example first. So imagine that you're given a word, so katsu, and a dictionary, right? And in the dictionary, the dictionary is super old and it doesn't have any labels, right? No index, no labels. So you can't really flip to the page that you want, right? So what you can do is that if you know these are the alphabets in the dictionary, what you can do is you can open the first page, right? And then you keep flipping. Right? So we're going to see A first, and then we're going to keep flipping until we see B, and then flip, 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 all the way until we see K, right? And this is what we call a linear search, right? Why? Because we're searching through it linearly, right? Sequentially, all the way from A, all the way through K, right? And the time complexity for this will be O of n, right? Because for linear situations where we don't have information about any of these, worst case, if our word is all the way at the back with the S, we're gonna go all the way from A all the way through S, right? So that is probably unideal. Another way that you could do it, probably, you guys are probably too young for this, but I think some people used to do this in their phone book, where you first open it in the middle, right? So in the middle, we'll see, in a dictionary, we'll see O, right? And then what's gonna happen is that you're gonna sing the alphabet song, right? And then what's gonna happen is that you're gonna realize K goes before O. So you're gonna flip the dictionary again, this time only focusing on the first half, right? So say you flip it into another half. So this half, we know that we can ignore it because L was after K, right? And then we are now at H, which is the middle between A and O. And we sing the alphabet song again, and we realize that H is before K, right? So by the same logic, we know that anything before H is invalidated. We don't need to look at it, right? And then we take the middle of H and O, and then we found our K, right? And this way, we're halving the interval by half every time, right? So the time complexity, can anyone tell me or guess what the time complexity of this type of search is?
O log n.
Yes, it's O log n, right? Why?
Because what's longer? It's like every time you reduce the power of available options.
Yeah, exactly. So we can actually write it out. So if we start with a number of samples, what's going to happen after our first iteration is that we're going to have it into n over 2, right? And then that is going to change to n over 4 after the second iteration, right? And what we can see is that this is a geometric sequence. So then our ideal search would be when we reach n over negative K is equal to 1, right? Where we have our target search. And then if you take the log of K, well, yeah, it's actually 2. Sorry. Yeah, so if you take log 2 and then you change things around, we'll have a time complexity of log base 2 over n. And since it's we're doing time complexities, we don't really care about log 2. We can change the basis it to 10. So that's usually what we end up with. And we like binary search because generally it's faster than linear search, right? Log n versus n, right? And so we found the word Katze in our German dictionary. And can anyone guess what it means? Out of curiosity, no? It means cat, because I like cats. Amazing. Okay, let's move on. Okay. So this is the general pseudocode for binary search. So we kind of explained it in a motivating example, but the pseudocode is basically, well, we have an array, we have to keep finding, so we have two bounds, right? We have a lower and we have an upper. And what's gonna happen is that we're gonna see if our target number is within that range. If it's not, then we know that if first of all, if our lower is greater than our upper, then something's wrong, right? So we can just exit. And then the second condition that we can look for is if our target is greater than our upper bound, right? Then in which case we know that we can just shift the whole interval. Or if our lower is greater than our target number, in which case we shift but to the other way. Or if they're equal, then we can just get the number that we wanted and do the operations that we needed. Questions? Amazing. Okay, so now the question is, binary search sounds super useful, right? But when do we use it? Do we use it when our data structure is linear? And also, what does linear mean in terms of data structure?
I guess you could say, well, there's only one dimension for data, so it's not like a 2D array for you. Well,
on the right track. So that's basically sort of the idea. For a linear data structure, we're thinking as actually a data structure that is storing things linearly, specifically sequentially. So even with a 2D or 3D array, if you've taken CS33, you know that they're stored contiguous in memory. So then that, in a sense, we still call it a linear data structure. A non-linear data structure would be, say, a tree, right? Where like it's sort of like it's not, you can't really go through it sequentially. So types of linear data structures are arrays, queues, stacks, and linked lists, if you can recall them from CS32. And now the question is, if we can search through them linearly, right? If we can use binary search in linear data structures, can we use binary search in all these data structures? No. Which ones can we not use?
Definitely not the linked list.
Right. So we can't really use binary search on a linked list because we can't random access it, right? Because we call from CS32 and 33 that linked lists are not stored, are not necessarily stored contiguously in memory. So then we can't really access one specific node without traversing to that node, right? So it doesn't make sense to binary search it. How about stacks and queues? Can we linear search that? Or can we binary search that? Okay, probably not. Why?
Like a workaround, you have like an extra way to temporarily store the elements, but
yeah. So sort of the same idea for stacks and queues. Recall from CS32 that stacks and queues are we can only access one end of the data structure. So queue is first in, first out, and stack is first in, last out. Last in, first out, right? So for stacks, we can always only access the last element. So there's no way for us to binary search unless we pop all the elements and search from there, right? And same thing for queue. So it doesn't really make sense, right? And now the question is, what's another property that we or I guess condition that we need in order for binary search to work? Can you think of any? One that's kind of obvious. Yes, right? It has to be sorted. Why? Because if I have like 1, 3, 2, and my condition, my lower bound is by the indices, then there's no way for me to move the indices, right? Because if it's not sorted, then we don't know. Now the question arises, what if I have a sorted array, but it's rotated? So let's read this practice problem, right? So if we have a sorted array, say 0, 1, 2, 4, 5, 6, 7, and we rotate it by k amount. So say it's now 4, 5, 6, 7, 0, 1, 2, right? And we want to find a target number. Is there any way for us to do it without using, well, there's one way that we can do it for sure, right? The most intuitive way that you can think of right now is a linear search, right? We can just go through it sequentially and find the index and return that. Is there any way we can make it faster, right? Say you're in an interview and the interviewer is like, okay, now optimize your code. We use the pivot. What does that mean?
It means you know that it's sorted, except like if you start the array at the pivot instead of like index 0, then and you like wrap around, then you know that the list is sorted in that manner. So you can use that path to do binary search.
That is very true, right? So like Lenny said, we have a pivot, right? And from that pivot, we can know that, say if we look at 0, we know that to the left of 0, we're incrementing, right? And to the right of 0, well, to the right of 0, we're decrementing, well, starting from 7, we're decrementing, right, strictly. So what we can know from that fact is that we can sort of still do binary search, but maybe with more conditions, right? So let's go through a visual example first, right? So say, well, this sort of looks the same, but we have 6, 7, 11, 12, 13, 17, 23, and then 0, 1, 2, 3. What's gonna happen is we can walk through it using normal binary search first, and then build our intuition from there, right? So what if we find the first middle point? So that's 17, right? But the thing is, we want to find 2. So normally, if we want to find 2, we just go to our right? Because 17 is greater than 2, so we can just go there. But in this case, the array is rotated, right? So is it necessarily to the right of us? No, right? Is it necessarily to the left of us? We don't know. But what's one thing that we can know? One thing we can know is that we can look at 6, right? We can look at our first element. If our first element is greater than 2, what do we know?
If it's in the array,
yeah. So if our first element is greater than the element that we want to find, it's probably on the left side, right? Because otherwise, because the array is still sorted, it's just rotated. So if the first element is greater, then we know that from the first element all the way to our middle point, which is also greater than our the number that which is also greater than our target value, is all strictly increasing, right? So we'll go to the left. But what if our first element is less than 2? Since it's sorted, yeah. Oh no, okay. Since it's sorted, we know that it must be lying in this range, right? So that's what's gonna happen. We're gonna look at the 2 ends, and then we're gonna realize that, wow, 6 is greater than 2. So we're in this region, right? And then we're gonna look at 23 and 3. We're gonna look at the middle value again, right? Which has a value of 1. 1 is surprisingly less than 2, right? So what do? Right, we go to the left, right? Because we look at 23, which is our new starting point. And 23 is greater than 2. So we go to our left. And then we find the middle point and we find 2, right? And so this is just binary search, right? We can build. So from this example, we can sort of know that this is just binary search, but with two more conditions, right? So we have, well, my left and right, well, my upper bound is, my lower bound is still less than or equal to my upper bound. Wait, less than my upper bound. What's gonna happen is that I'm gonna find the middle value. I'm gonna compare against my target value, right? And then if it's the same, we're done, we're happy, we return. If it's not, right, if the middle value is greater than our current value, what do we want to do?
Sorry, could you repeat that?
Oh yeah, okay. So if our middle value, right, is greater than our target value, what do we do?
Like the very start, 17.
Yeah.
If it's greater, then typically it goes to the left. But you'd examine first out, I guess above the pivot.
Yeah,
So
exactly. Exactly. So within our binary search, our original binary search, we actually need to add two, well, one if else condition, right? So we compare with our lower bound. If it's greater, if our lower bound is also greater than our target value, we go to the left. Otherwise, we stay at the right. And the same thing applies for the other side, right? Because if, for example, we're searching for 7, right? We're looking at 17 and we're looking for 7. We look at 3, right? 3 is less than, so we know it should be on this side. But if we're looking for 23, we know that. If we're looking for 23, we know that 6 is less than 23, so we know it should be on that side, right? So the pseudocode, actually the code for this solution is just normal binary search, right? The if else, and then within it, we have our searching condition, right? So the extra bounds. Okay. Then let's move on to another cool problem.
All right, that's my turn to tag in. I'm Suhas. I'm going to be leading for the next 30 minutes-ish. And I wanted to cover this problem, which is, if you came to our first workshop, it may look slightly familiar, but even still, it basically reads that we are given an n by m matrix where all the rows are individually sorted in increasing order, and the elements of a row are smaller than the elements of the subsequent row. And given this two-dimensional array, we want to determine if an element exists in this problem. Now, just to start off with, I want to kind of go through the interview checklist, so to speak, of the kind of steps that you would want to take anytime you face an interview problem. And the first step is to identify the key information within the problem. So I've taken the liberty of bolding it. So you're given an n by m matrix. There's nothing really to glean from that, but it is important to just know your size. You're given the fact that every row is sorted in increasing order. So what that means is if we focus on a single row, 10, 12, 15, 18, 19, we see that this row here is sorted. And finally, we're given the fact that the elements of a row are all smaller than the elements of the subsequent row. So what that means is any element in this first row will be less than any element in the second row, will be less than any element in the third row, and so on and so forth, such that 10 is less than 27, is less than 52, and so on. And what we want to do is determine if an element exists. In this case, it's 68, and we see that it does work. And the most naive solution here is, like normal problems, we just do a linear search. We go through every single row, every single column until we find 68. Now, obviously, we're in a binary search lecture, and that obviously sounds a little bit slow. So let's try and think of some ways that we can optimize this. So are there any like solutions that are jumping out to either of you just from reading the problem that might be a good starting point? Yeah?
Binary search the first column. Binary search.
Okay, so perfect. So essentially what Felix said is that we have a column, our first column over here, And what we can do is we can binary search for this number, determine where we land in here, and then look through that row of the array and then binary search through that. Is that what you said? So do you want to just elaborate on how you would binary search for an element that doesn't exist in the column? Like in this case, 68 doesn't exist. So how do we know where to start?
Well, if you're looking for 68, then like, you just keep going until you find one that's bigger than 68. And then you go back.
All right, so what you're saying is linear. So scan through this first column.
Or like you can do this with binary search. Like, oh, it's bigger than 68. Then you just like jump halfway.
Exactly. So that actually leads me to another cool thing about binary search, which is that your element doesn't always have to exist in the array. Oftentimes, binary search, if you apply it on an array where your element does not exist, applying the exact same binary search code, it'll take you to the very first element that is less than the element that you are looking for. So in fact, what you were suggesting, Felix, is that you binary search over here, you binary search over here, and then that will effectively get you your solution. And that honestly works. Like you could very well do that. There's no issue in doing that. I guess another way you could do it is that the kind of fun way approach that I like to do for this is that when you're given a problem like this, it helps to just break it down, sometimes see it the way that your computer sees it. So like Katie originally touched on, all of this is going to be stored in one contiguous block of memory. And you notice that if we look at 25, the first element of the second row, and we look at 19, which is the last element of the first row, 25 is greater than 19, 50 is greater than 45, 62 is greater than 60. So if we kind of piece these rows together into one single row, like the computer would see it, we just get one giant sorted array. And this kind of leads us to an approach where you can just binary search through the entire one-dimensional array by flattening it. And I'm just out of curiosity, are you guys familiar with like how to calculate an index, like how to translate any number from 0 to n times m into like an index on this array? Do you want to just like give an example?
So I think it's like, we'll say I is the ij, whatever. It's like I times the size of the data, which would be integers in this case, times the amount of elements in m, I guess, or whatever, plus.
No, you're good.
I times n times the data size plus j times, or plus j times the data size.
Yeah, pretty much. You can just take I times the n, which is the number of rows, plus j times, and then that will just get you to where you need to go. I times the number of rows and then j to get to the column. Or I times the columns and then j to get to the row. Yeah. So yeah, you can use that. You can essentially use that to get to where you need to go. Katie, can you unlock things? So that was just a quick practice problem, but I think oftentimes when we talk about binary search, our view of binary search is quite limited. We are so used to seeing binary search be used to search for an element in an array that I think we've kind of put up the blinders to what binary search can actually be used for. So what I'm going to be talking about is binary search in the most general context and how binary search was effectively intended to be used. And that is related to something called a monotonic function. So what does that mean? A monotonic function, to put it in more layman's terms, is a function that is either entirely non-increasing or entirely non-decreasing. In math terms, this would mean that the first derivative never changes signs. And just to kind of show what that means on a monotonic graph right here, notice how when we go from the left point to the right point, our y value is always increasing or staying the same. It never decreases. So like the first derivative is always going to be non-negative because we're never having a point on the graph where we decrease. So it's just a quick definition to get out of the way that is going to be very helpful for when we talk about how we use binary search. So let's take a look at this graph. What we have right here is a target, just like you would in any normal binary search code. but I want to kind of generalize this. So we have this y-axis, which represents a set of values. And what we want to do is we want to find this target in the y value of this graph. So all this is a function that maps an x value to a y coordinate. And we want to find the x value that maps to this target coordinate. So what do? Well, we know the x value at the start over here. We know the x value at the end over here. So what we can do is we can pick the middle x coordinate, which leads us right here. Now, what do we know about this y coordinate relative to our target? It's greater. And what we also know is that this function is monotonic, which means from this point to the end, this function is only ever going to increase. And from this point towards the beginning, we know that the function will only decrease. It only operates in one direction. So that means that when we're considering the search space of this minimum x to this maximum x, now that we have picked this point and evaluated that it is greater than our target, we can shift where our maximum x is to that point. A concept very similar to binary search, but it's just a little more generalized. And that small bit of generalization is what will give us a lot of power in solving future problems. You notice that if we were to continue this algorithm and repeat it, so on and so forth, we would eventually find some middle point that converges onto the target that we want. And that's what binary search is all about. It's about converging onto the point that we want. So here is a quick little question, which is determine where the following functions intersect. y1 equals arctan of x, and y2 equals x minus 2 cubed minus 8. Now, if you're really good at math, you can try doing some equality. Tan negative 1 of x equals x minus 2 cubed minus 8. You know, take the inverse tan of both sides or tan of both sides and get this complicated expression that's probably still not solvable because I don't know what the heck that is. And I'm not sure if many people would. So it's kind of clear that math is not going to be our friend here. So why do math when we have a computer that can do our math calculations for us? Exactly. So how do we know when two functions intersect? Is there like a more neat definition we can give to intersecting functions? The difference is 0. So if we were to take y1 minus y2, we would get 0. That's effectively the definition of when two functions intersect. So let's graph that. Let's graph a new line. Y equals y2 minus y1. And we get kind of this function over here. Now, the first question we want to ask ourselves is we wanted to create a monotonic function because this is a binary search question. Have we created a monotonic function here? Is it entirely non-increasing or entirely non-decreasing? I see a couple of nods. Okay, cool. So we know that we have created a monotonic function. So that's good. But now what do we want to do? We want to find the point, the x coordinate, where this is equal to 0. So like before, maybe I know that this is going to be greater than 0. And from observation, I'll just say that it's less than 5. So what I know from this is I have a start bound and I have an end bound. And I want to find the point at which this is 0. So like before, I can just binary search. I pick the middle. I see that this is going to be some super negative value. So I clearly want to move to the right. And I can shift this point to the right until I get here. I can pick the middle again. I'm still negative. So I want to shift that point to the right, and so on and so forth. And over time, these two circles will begin to converge right at the point that I want, which is the point of intersection. So effectively, this is a way that we can calculate the intersection of two lines given their equations. And in fact, I don't know, have either of you used a graphing calculator's intersection function before? No? Basically, the way it works is that you specify a left bound, you specify a right bound, and it'll tell you exactly where the intersection is in the middle. It uses a process very similar to this, where it uses the left and right bound to try and figure out where the intersection of the two functions are. So now I want to move into a more concrete practice problem. And this time I want to talk about graphs. So let us suppose you have a weighted connected graph. We want to find the minimum value k, such that if all the edges with a weight greater than k were removed, this graph would still be connected. So let's just take a look at what that means. So what exactly does that mean? Well, let's say k equals 4, right? If I removed all the edges with a weight greater than 4, I would remove this edge, and I would remove this edge, and I would get a graph that looks like this. I won't label the edge lengths. Now, what exactly is a connected graph? In case you are unfamiliar, a connected graph just means that I have a path from any node to any other node. So this graph right here would be connected because there's no isolated node. I can reach every node from one to another. So this is a connected graph. Now, what if I were to remove, say, 2? If I remove all edges greater than 2, what would happen? Well, I would remove this, 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 and this, and I would effectively be left with the following graph. So now in this case, we have 2 isolated vertices, and they're isolated because they have no edges connecting them, which means that this graph is not connected. Now, if I were to have picked what I'm going to tell you is the optimal k value, which is 3, what I would have gotten is I would have removed this edge, and this edge, and I would have gotten this graph. And notice that this graph has an edge between all nodes. This is connected. And so we see that k equals 3 is the optimal value of k. And that's what we're trying to find in this problem. The optimal value of k, such that if all of those edges were removed, the graph would still be connected. So are there any questions about the problem before we move on? Okay. So the solution idea, we clearly want to use binary search. So what I was thinking is that we use binary search on the value of k. And we will show why a little more clearly later. But for now, I feel like that's what I want to find, right? That's the answer. So it makes sense to binary search on that. So what condition lets us know if we need to increase our lower bound or decrease our upper bound? Remember that in any binary search function, I always start with the low value and I end with the high value. And then over time, I pick the middle, I set that to the high, and so on and so forth until I narrow myself down to the value that I want. So in this case, I know that the search space, the minimum value that I can pick for k is whatever the minimum value of my edges are. So that'll just be the min edge. And I know my upper bound is similarly bounded, which is the maximum edge. So I know I have a minimum and a maximum that my value of k can be. But how do I determine, once I pick a middle value, if that works or not, or if I need to lower my max edge bound here, or if I need to move my min edge bound up there? And I would just say, remember the examples on k equals 4, k equals 2, and k equals 3. How are we able to determine if we needed to go up or down based on the results that we got from k equals 4, 2, and 3? What was the condition that needed to be satisfied?
Yeah, well, if we're able to measure how many isolated nodes there are, that's one.
Exactly. Just the measuring of whether the graph is connected or not was enough to let us know if a value worked. For example, if a graph was connected for 4, I would try it on k equals 3, because I know that if a graph works, if a graph is connected at k equals 4, that graph will also be connected for k equals 5. Because increasing that bound for k and removing less edges won't make it any less connected. So I know that I would want to decrease it from there. So we know that we want connectedness to serve as whether we increase or decrease our bounds. So if the graph is connected, do we want to decrease our maximum or increase our minimum if the graph is connected? So if k equals 4 is valid, do we want to start going to higher values of k or lower values of k? Huh?
Decrease.
Decrease. We want to decrease the max edge if the graph is connected. We want to increase the min edge if the graph is not connected. And that was kind of the intuition that we found. And I don't know how familiar you are with graph algorithms, but if we want to determine whether a graph is connected or not, we can use something called a depth first search or a DFS to basically say, hey, can we visit every single node in one traversal, or can we just like walk around and get to every node? And if we can, the graph is connected. If we can't, the graph is not. And so we want to test connectedness using a depth first search. So now I kind of want to just talk a little bit about the intuition of using a binary search on K. And that is this graph monotonic? So we talked about how a graph is either connected or not. And depending on if the graph is connected, we want to decrease the bound. If the graph is not connected, we want to increase the bound. So we know that it either is connected or it either is connected or it isn't connected. So we kind of have two states that the graph can be in, a 0 or a 1. So is this graph monotonic? And that's kind of the real question. Well, interestingly enough, you notice that the slope of this graph or this line here is 0. The slope of this line here is 0. So yeah, technically by the book definition of monotonic, the derivative never changes sign, right? It never goes from a positive to a negative or negative to a positive. So it makes sense that from a book definition standpoint, this graph is monotonic. But how does that line up with binary search? Well, the idea of binary search of taking the middle and jumping back and forth if it's less than or greater than is kind of misleading in my opinion, because yes, you want to do that. You want to get to this value of 4. But again, it's kind of like we're never going to reach the value of 4 sometimes. We're just going to have to like slowly inch our way towards there with the bounds. And what I mean by that is, yes, even though we want to be conservative about this, that's the best way of putting this, which is that we know that 4, or I just used 4 as a random example in this graph, but we know that this value here does work, right? So what we want to do is we want to decrease our top bound here, but we don't want to overshoot it. And let me see if I can find an example of what I mean from earlier, which is the binary search pseudocode. Okay, so when we are used to seeing binary search, I hope this code doesn't look too unfamiliar. We're always used to seeing this code. When we want to reset the lower bound or reset the upper bound, we want to set it to the midpoint +1, or we want to set it to the midpoint -1. The rationale for that being that whenever we have an array where our element exists, if we pick an element like H and we see that H is not our element, there's no reason to still include H in our search space. It's completely disregarded. We know H is not our element, so we'll just discard it. And instead of moving the lower bound to the middle, we'll move it to the middle +1. So that's why we do that in our code for binary search, where the element exists. But what if the element does not exist? Or what if we're using functions where it's not exactly going to be integers? The reason I bring that up is because in this case, if we were to have picked 4 at the very beginning, we know that 4 is valid, but we're not sure if 4 is actually our solution. We have no way of determining what makes this any different than this, because these are all connected. So what we do is we still include 4 in our search space, despite decreasing the upper bound. So we went from 0 to 8 And now we're going to translate it 0 to 4. So when we picked 4, we had no way of knowing that 4 is actually the valid solution. All we knew is that it does work. So we know that our search space doesn't need to include any of the elements above 4, but we still want to include 4 in that range. And then from there on, it works very similar to binary search, which is like we go to 2, we see that 2 doesn't work. So we change it 2 to 4, changes 3 to 4, 3.5 to 4. Notice we're starting to use decimals. And now the question becomes, when do I terminate? And the fun answer to that is that there is no neat way to determine when to terminate. Oftentimes with functions like this, like if I wanted to determine where this function actually touches 0, it's going to be some irrational number with an infinite amount of points after the decimal place. So it's not like we can obviously extrapolate that to the infinitesimal decimal places that we want, but what we can do is we can get as precise as possible. So we're going to have just a bit more to talk about in terms of how the system treats numbers. But when the system is treating any numbers, all numbers have a certain precision. And what this means is that numbers, like when they're stored on our computer, cannot be infinitely precise. They cannot have all the decimal places possible. And so regardless of what we want, like even if we wanted infinite decimal places, it's not like we could get it. So oftentimes what we do is we just say we want to terminate when the left bound and the right bound are around like, I don't know, 10 to the power of -6 apart. So we just pick a small value and that way we'll get this much precision. So that is kind of how we determine when to terminate it. So yeah, even though 3.5 to 4, we'll go to 3.75 to 4, we'll go to like way more decimal places to 4. We know that this difference between these two values are getting infinitesimally small. And so we can pick a value like that. So just what that means in terms of the binary search pseudocode, should have probably just included this so you guys don't have to see that flash by every time. Normally what we do is while the target is not found, or sometimes we even have a check of if the upper bound is less than the lower bound. Instead, what we can do is just check if the upper bound minus the lower bound is greater than 10 to the -6. And that becomes our condition. So I know that was a bit of like a tangent on things like precision and stuff that might not seem as related to binary search, but I just wanted to get across this point that like the usual convention of binary search, you just need to tweak it a little and then you're brought to like the more general form of binary search that applies to so many different problems. And so I'll pass it off to Kate for binary search.
All right. Yay. Okay. So after that amazing presentation on monotonic functions, we're going to talk about our favorite type of trees, binary search trees. So binary search trees, what are they? So from their name, we can sort of know that binary. So for each node, we have 2 children, right? Usually we denote them or we call them left and right node, right? And search, we usually, well, okay. So a binary search tree is binary, right? So we have 2 nodes. And it's called search because we usually use it for ease of access, insertion, and deletion. So what that means is that we have this very important property where our left node is strictly less than our current node, and the value of our right node is strictly greater than our current node, right? So if we look at our example, we know that 8 is pointing to 3, right? So our right node, which is strictly less. And then we have 10, which is strictly greater, right? And other implementations, sometimes they allow for repetitions. So then they'll usually put less than or equal to on the right. And then the other side is strictly less than, right? And so with that in mind, what can we tell? And probably, preferably, if you came to our workshop on our second workshop, what can you tell me about the properties of the subtrees of our binary search tree? What properties would they have? So if we look at our tree, right, this tree, what one valid subtree would be 3, 1, 6, 4, 7, right? What is the property of this subtree specifically? And can we generalize it? Yes. So for each tree, its subtrees should also be a binary search tree. This is a very important property, and I keep emphasizing on this property because this is what, I guess this is how we differentiate it from other trees, and this will be the important factor that we consider when we are doing problems, right? And one thing that we need to think about right now is that how are binary search trees different from normal binary trees, other than the word search? Yes, exactly. So for a binary tree, we can sort of guess from its name that a binary tree is a tree that has 2 nodes, right? So that so we can have either 0, 1, or 2 children per node. But the thing is, it's not necessarily sorted, and that's the difference between a binary search tree and a binary tree. And this property is very important because having the ability to differentiate from left and right, so having a sorted property is going to help us with time complexities, as we'll see later. And usually when we're talking about binary search trees, we think about self-balancing binary trees, which is basically a binary tree that is always balanced. So when we're inserting and deleting, it still looks like a very balanced binary tree. And now the question is, what is a balanced binary tree, right? As a matter of fact, we can have many types of binary search trees. One of them is full. Full just means that for every non-leaf nodes, we have 2 children. And for leaf nodes, we have 0 children, right? Because leaf nodes, as you can recall, are nodes that have no children. And for complete, all the levels are completely filled, right? Except the last layer, right? And on the last layer, all the nodes should be aligned to the right, is by definition. And a perfect tree would be a tree that is complete and full. And then a balanced tree would mean that the height of the left and right subtree have a difference of most 1, right? And this is important because what happens if we don't have a balanced tree? What's the worst case? Worst type of tree? Yes, it becomes linear. Specifically, they call it a degenerate tree. So basically, it just looks like a lengthless, right? And that does not help us with time complexity because we still have to traverse through the whole thing in order to get whatever we want, right? So that's unideal. So with the properties in mind, let's go through the time complexities of a binary search tree, right? So can you tell me the insertion for a balanced binary search tree, the time complexity of it? Log n, right? And why is that?
Say the searching of all and then reduce by half each time.
Exactly. And how about for arrays?
Is the array sorted?
Doesn't really matter in this case. We're just like inserting normally. But we're thinking about worst case is the keyword. Yeah, okay. So I'm going to repeat for people who might potentially look at the recording. So a balanced binary search tree has a log n time complexity for insertion is because we need to insert at the right place, right? We need to follow its property where our rightmost node has, our right node has value less than our current node, and which has a value less than our left node, right? So we need to first find its placement and then insert it, which will take us time of log n because we need to traverse through the tree. But each time we can just take a subtree, right? Because the subtree also has the same property. Whereas for arrays for insertion, if the array size is not big enough, like the memory size that we allocated for arrays isn't big enough, we need to reallocate the whole chunk of memory and copy everything in, right? Or say, for example, if we want to insert at not the last element, right? So at placement I, or like say position 0, then we need to move all the array elements, right? So worst case would be O of n. And the same thing goes for deletion, because deletion is sort of just insertion but inverted. And how about for accessing?
Just like reading the values.
Mm-hmm.
Say log n,
Mm-hmm.
and depending whether it's for log n or
Okay. Oh, actually, what I was trying to look for is finding the ith element, not necessarily like this specific element, but that would be, yeah, but that would be correct. So for arrays, it would be O of 1 or constant, because we arrays, recall that they are stored contiguously in memory. So we can just go to that position and get that element and just read it, right? So that'll be constant. But for a tree, we can't do that. They're like linked lists, but slightly better. So we still have to do the traversal each time, but it's O of log n, so not exactly too bad. And with those in mind, let's do a small warm-up problem, right? So if we have binary search tree, how do we find the k smallest node? Just, yeah, how do we find it? Ideas.
so basically you would go to the smallest element, select post, and then just go.
Yeah, exactly. So what we can do is we can first look at the problem and think about what we need to do, right? So if we look at, say, if we look at this example, we know that it's a binary search tree. So 28, 4, and then 12, you know, it's like that. And say, if we want to look at the third smallest element, we look at it, and then we know that it's 10, right? And how do we do it in, I guess, in our head is that we first find the smallest element, right? And then we find the second smallest, and then we find the third. And then since it's the third, which is the one that we want, we just return this value, right? So the summary for what we want to do is we want to read it from smallest to largest, right? Like what you said. And then we just return when our read count is equal to k. But how do we put it into C++ syntax? Ideas? So first step first, right? How do we read from smallest to largest? What type of traversal is that? Memory retrieval from CS32, right? So we're reading from right and then to ourselves and then left, right? So if we were to choose from pre-order, in order, and post-order traversal, which one would we choose? You have 1/3 probability of getting it right.
Probably. Well, pre-order. Oh no.
It's right and then middle and then left. So is it pre-order, in order, or post-order? What's that?
Why is it
right to left?
Left to right.
Oh, I think we're.
Yeah, I think it's because like you're facing.
Oh, sorry. Okay, from left to right. Yes. So that is called in order. And how do we keep count, right? So how do we do the second step? How do we return when the number of elements we read is equal to k? Sure, or we can just, in other words, have a variable, right? That keeps track, right? So if our variable is equal to k, we can just return that value, right? Otherwise we keep going. So then this would be the code for that problem. So what's gonna happen is that if our root is null, we can just return, right? That's an edge case. Otherwise, we're gonna call ourselves recursively from left to middle to right, because we're doing an order traversal. And we have a count for k, where k is the kth smallest number that we want to read. And then we just decrement k all the way until we want it's equal to 0. That means that we've read it that number of times, right? So we're at the position that we want it. We can just return it, right? And then, so it's like left, center, and then right. Yeah, questions? Fine. Okay. Okay, now we're gonna move on to a slightly harder problem because we have time. Okay, so what if now we want to count the number of subtrees in a binary search tree whose nodes lie within a given range, right? So if say we have the same tree as before and we have a given range, how would we find the numbers of subtrees that fit in that range? Do we have any intuitive ideas? Wait, I'm sorry, can you speak slightly louder?
Is this the same as finding the number of nodes that lie between 10 and 15? It's like a subtree with how to do that.
That would be slightly correct, but not exactly, right? Because we want subtrees. So subtrees, 10 is itself a subtree, right? Where and 12, 10, and 14 is also a subtree. We'll have 2 minutes to think about this problem. Exactly.
So same thing on the right.
Right, yeah. But how do we find, so you say start with a node that is within range, right? How do we find that node that is within range? The idea is there.
You start with 20, right? And then like 20 is like between 10 and 15. That should just be at the and then we know that we can't go to the right because 20 is larger than 30. So you only go to the left. And then from there it's like less than 8, less than 8.
That is on the right track, but I think that makes things slightly more difficult because you're building it from, I guess, the top level, right? So what's going to happen is that we look at 20 and then we compare, right? 20 is greater than 2, is out of range. So we just don't consider it and we go to the right, which is the right idea. And 8 is within range, right? But what if we have 22 here, right? Then this is not a valid subtree, right? So it'll be sort of hard to calculate. But so the idea is, what do we do it button up, right? So the idea, yes?
Sorry. So but 8 forward would be a valid subtree, but we don't.
Oh, we have to include all the nodes that are, I guess, within the tree. Yeah, sorry if that wasn't too clear. So, but that is on the right track, except we reverse it. So what's going to happen is that what if we look at the leaf nodes first? So say we look at 10, which is a leaf node, and 10, we see that it's within range. So we mark it as within range, right? And then we look at another leaf node, say 22. And 22 is sadly not within range, right? And then we keep track of that. Then what's gonna happen is that we look at all the rest of the leaf nodes and we realize that 14 is within range, and so it's 4, right? And from there, we can start building our subtrees, right? Because for our leaf nodes, the subtree is just ourselves. And for the node that is one layer above us, the subtree would be that node plus its baby nodes, right? Leaf nodes, not babies. Right. So we know that 14 and 10 are valid leaf nodes. So we know that 12, which itself is within range, because 14 is, we know that binary tree's property is that the left side has, or I guess the right side contains a greater value, right? So if 14 is within range, then we know that this subtree is also valid. So currently we have 3 valid subtrees, right? And then from there, we call that 4 is a valid leaf node. And so with this valid subtree that we just found, we can construct a bigger subtree that is also valid, right? And then finally, we look at 22, which forms the whole tree, which is a subtree of itself, right? And that is invalid because 22 is out of bound, right? So then this is not a valid subtree because 22 is not. So the idea is to look at the leaf nodes and then building our way up. So the code would be this, where there are a couple of things that we have to keep track of. One is whether or not our left and right subtrees are valid subtrees. The other one is the number of subtrees that are valid currently, because we're building our way up, right? We don't want to lose track. And then the third one is our interval, right? That we want to keep track of. So then what's going to happen is that we're going to build it recursively and look at our left and right? And make sure that they are valid. And if our left and right are valid, we compare to see if our center node is within range. And if it is, we increment our counter and we send it up to send it one level up. Yeah, okay, amazing.